All right, let's move on to BJTs now. Okay, let's now, so for those of you who are not familiar with the term BJT, remember the transistors are of different kinds and types. For this course, we are going to mostly focus on the BJTs, but once you know the working construction and functionality of BJT, the other transistors are pretty much same, okay? So BJT stands for bipolar junction transistors, okay? The reason it's called bipolar is because if you recall the diode had one junction, right? You had a p-type material, you had an n-type material, and then this is what we refer to as a junction, correct? And then, you know, across this diode, because this was a p-type material, so this had a lot of holes in there, correct? A lot of holes in there, and here you had a lot of electrons here because this was a negative. So because of the force of attraction between the two opposite charge material, this electrons will move here and then will make a wall like this. And similarly, this positive charge here, they will move to the other side and they will make a depletion region, okay? This depletion region will basically act as a resistance. And then the wider it is, the higher the resistance. And because this is very small width, so this resistance is going to be lower, okay? In a transistor, you'll have two junctions, not one, unlike diode, okay? So keep that in mind. That's why it's referred to as the bipolar junction transistor. So what are the two types, PNP and NPN? What is the difference between the two? In a PNP transistor, holes take part in conduction, sorry about that. Okay, conduction, and then NPN, electrons take part in conduction. Okay, so which one is better, PNP or NPN? Remember, what was the characteristics of the electrons? Electrons have what? Electrons have 2.5 times more mobility than holes. They run faster, okay? So if you're going to use this device for a switching application, you need to turn on and off something like a foot thermostat or emergency alarm or something. You want that to be done as quickly as possible. So you prefer NPN, okay? They are 2.5 times faster. Okay, but the way they work, construction is different, but the way they work and what they do as a job is same. Okay, it's just the construction is a little different. So we'll see how both PNP and NPN looks like. So if you look at the top graphics in the top right, this is PNP. Okay, PNP basically means you have p-type material, you have n-type material, and you have p-type material. So you sandwich them together, and that's what makes a p-type material. Okay, so you got two junctions here, right? You got this junction over here, this, and then you got this junction between N and P, okay? So maybe I can refer to it as a J1, and then this referred to as a J2, okay? This J1 junction is between which terminals? This is between E and B terminals, okay? This is your E, this is your B right here, and then you got C, okay? And then this junction J2 is between C and B, okay? So diode with a two-terminal device, transistor is a three-terminal device. It has three terminals. One is the emitter terminal, okay? And emitter terminal is large in size and moderately doped, actually highly doped. Base terminal, which is this base right here, okay, this is very small in size. And you can see, you know, the base is how much? 0.001 inches, and the rest of it, the total width of the transistor is 0.150 inches, or it's written over here. So base is very, very small and very lightly. Collector, which is C here, This is collector, as the name suggests. This is where you collect the um, current. Okay, that's what. So it's almost also your output. So collector is also moderate in size and moderately low. We usually so if you see the J1 junction, we want our J1 junction to work in forward bias condition, and we want our J2 junction to work as a reverse bias region. That is when our transistor work as an amplifier. Okay, now if I need to use my transistor as an amplifier, I need to make sure that both junctions are set to these forward bias and reverse bias. So let's learn about first, how can I set J1 to forward bias region? Okay, all right. What is this material? Yes, folks. This is a p-type material, right? It's a p-type material. In order for me to make this p-type material, I want you to think of a diode here. You got p-type material, you got n-type material, and then you can again p here. The positive terminal of the diode needs to be connected to what terminal of the battery here, such that the polarity matches. Because when the polarity matches, that's when the diode work in a forward bias. So what should be the polarity? So if I have this plate, which is bigger than this plate, we know that this is positive, this is negative. So you got positive going in here, you got positive going in here. P is positive too. So you have a polarity match or polarity mismatch here. You have a polar match here, right? So this is going to work in a forward bias condition or region, okay? Let's now move on to uh, the right part of the graphics, where you see you have the N here and then you have the P here. So this is P positive here. And then you have negative terminal here, because this is a smaller plate, this is a bigger plate. Bigger plate is positively charged, smaller plate is negatively charged. So you have negative here, correct? Negative, negative, negative. So you have a negative here and then you have a positive here. There is a polarity mismatch here. That means this junction right here is going to be in a forward bias region or a reverse bias region. Reverse bias region, okay? And it's going to be in a reverse bias region. And just to, so we know how we can set the polarities of these voltages in order for these junctions to operate in this region. And when they operate in region, they work as an amplifier, and I'll explain you how this is working. Just to make sure that in forward bias, although we have covered it in the previous presentation, but let's just say in a forward bias region, the depletion region is small or big? Small, right? Because in a forward bias region, it conducts, current conducts. In a reverse bias region, current does not conduct, right? So the depletion region in this case is big. Smaller depletion region means resistance is very low. Depletion region is big, resistance is very high. Okay, and then similarly over here, if you, this was the PNP transistor over here. If you have an NPN transistor over here, you basically have NP and N sandwiched together. And again, remember this junction right here, which is J1, this needs to be forward bias, right? Forward bias. So the polarity over here, which is negative, need to match with the polarity over here, negative, correct? So this negative, this means this is going to be a small plate negative, and this is going to be the plus. This junction over here, right here, this need to operate in reverse bias if you want to use the transistor as an amplifier. So the polarity needs to be mismatched. So because you got N-type material here, which is negative charge carriers, so therefore the polarity over here needs to be positive. So therefore you have a positive plate here and then negative here. Okay, so how would you bias a PNP transistor or an NP transistor? Well, the way you bias is depends upon what is the application of the transistor. If you're going to use it for amplifier, then you have to make sure that the junction 1 is going to be forward bias and junction 2 is going to be reverse bias, and therefore that's how we choose the polarity over here. Okay, now let's move on to see how things work. Transistor operation with the external sources VEE and VCC, which is basically this right here. Okay, VEE VCC connected as shown. The emitter base junction is forward bias. Emitter base junction is this junction right here, which is this right here. And I can also write JEB, emitter base junction, JEB. Because I have positive here and I have p-type material here, which is also positively charged, right? So therefore positive and positive match, so it works in a forward bias region. And in a forward bias region, the depletion region is very small, like it appears on the screen. Okay, in this region over here, it says the base collector junction is reverse bias. You have base here, collector base, and then this is going to be reverse bias. This was forward bias, so there has to be a mismatch because this is plus here, so this needs to be negative, right? And therefore it's connected to negative, positive. Okay, got it. Now what is going to happen here? What is going to happen? I'm telling you here, explaining you the transistor operation. Okay, so try to give your focus here. And it's basically building up the same concept that we had for the diode. Okay, you have positive charge carriers here. Why do we have positive charge carrier here, folks? Because this is a p-type material. You have n-type material here, which is negative electrons, negative electrons, negative electrons. Okay, and then you have a lot of positive electrons here again, because this is a collector terminal. This is where you collect the current. Okay, with positive charge over here, with positive charge over here, what is going to happen to these majority carriers here? They are going to repel, or they are going to be attracted towards each other. So extremely strong pressure applied through the help of this external battery, which is positive, and then you got this positive charge carriers in excess because this material has been doped, majority carriers positive, they are going to repel each other, so they are going to push, they are going to move in this direction, correct? Okay, all right. What happens when all these positive charge carriers, all these positive charge carriers, they go into this base? This is the base, right? And remember what I mentioned here, that your base is very small and it's very lightly doped. Okay, okay. You have these excess electrons moving into the base. What would happen? Will they be able to attract with the electrons? And if yes, what would happen to these extra holes? Because say number of electrons here is 1, 2, 3, 4, 5, 6. So there's 6 electrons here in the base. Okay, I got say 20 holes over here. So there are 20 holes here and then 6 electrons. These 6 electrons will actually get recombined or get attracted towards 6 of these holes, but we still have 14 positively charged carriers here. What would happen to them? They can't stay there, right? These positive charge carriers in yellow, 14 of them, I'm just trying to put a numeric value to them so you can understand, but this number is going to be in billions and trillions, right? So these 14 positive charge carriers, they are squeezed in that small area. They cannot recombine with any of the electrons because all the electrons have been soaked up by these positive charge carriers. They will actually go past this depletion region, okay? They will go past this depletion region, get to the collector terminal over here, where all this current will be collected, okay? A very tiny amount of electrons, because you see, you got positive charge carriers here in the base region, and the base is connected to negative here, right? So very tiny amount of voltage will go here, but this will be almost, you know, zero. You, in reality, it's going to be in few microamps. Okay, we refer to as IB, which is the base current. The collector current IE over here is the current that is basically the total number of majority carriers that are flowing uh, from here. And then in the collector region over here, all these plus sign, which were 14 of them, which are now going to move over here, they are collected uh, as a collector current, which we refer to as IC. So if you look at it, the flow of the current is such that you have, it's going like this, right? This is your IE, okay? Part of it goes here, which is IB, and then most of it goes here, which is IC. So if we do the math, or KCL basically, we get the equation IE equals to IB plus IC, okay, where IE is the collector current right here. This is the collector current, this is the base current, and this is going to be, sorry, this is the emitter current IE, this is the collector current IC, and this is the base current. This current is going to be few microamps, almost close to zero, and this IC is going to be milliamps, okay? And if you add the two, it should give you this number IE, which is again going to be in milliamps. So that's how the transistor is going to function, and that's how it's going to, the flow of the current is going to be such, okay? And it all depends upon these polarities, okay? So this IC over here, folks, again, this is important here. IE emitter current, which is the total current right here, correct? It's the total current that's flowing over here. And the equation we got equals to IB plus IC. Because this number is extremely small in microamperes, we can also write it down that IE is approximately equal to IC, correct? Okay. Also notice here, because this junction was forward biased, so the depletion layer was very small, less resistance, and therefore the carriers will go past it. But here, because we had the junction in a reverse bias, so the junction the depletion layer was big, the width of the layer was high, and therefore the resistance was high. But if you notice, we still got IC here. We still got IC over here, which is again almost equivalent to IE, which is over here. Okay, so what we are learning here, even though the resistance here is small and resistance over here is big, two different resistance, but we still get the same amount of current. Okay, in other words, what I'm trying to say here is that you have some resistance here. Okay, this resistance is associated with this depletion region on in a forward bias, and this is going to be, say, R, very small. It's very small because, and this is your IE, correct? And then you have this region over here. This resistance, I'm going to say R in caps. And this resistance, because you have the depletion region, which is a very big one, we have R is going to be high, but you still have the same current that's flowing here, IC, which again, they both are equal. Okay, so if I measure voltage over here, okay, so I get V equals to IE times R, okay, and if I calculate voltage over here, okay, so I get what? V equals to IC times R, right? Remember, this R is very small, so V is going to be small, correct? Because this R is going to be smaller. But over here, because this R is going to be high because of the depletion region, which is big here, this V is going to be bigger. So this being smaller, this being bigger, you have basically amplified the voltage. Are you guys following me here? Because of this deflation region having the two different kind of resistance, but current being same, we are able to amplify the input voltage and magnify it many times. So V is up, and we know the gain is basically a ratio of V naught over Vn. In this case, this is our V naught, right? Because this is connected to V naught, and this is your Vn right here. So V, and this is here is Vn, okay? So if this number is bigger, V naught, and this number is smaller, so your gain is going to be greater than 1, right? Okay. So similar concept of the operational amplifier that we bring over here in transistor, but the difference between the operational amplifier and the transistor is transistor has a lot of components that we will learn on Thursday. Those parameters are dependent upon how the gain is decided, or how the you know uh, how the signal is amplified. Also remember, when we were learning about the gain for the operational amplifier, it was in very high number, 10 to the power 5 to 10 to the power 8, right? In case of the transistor, that gain, we usually refer it to beta, is going to be a very small number. It's going to be 45 to 400. So if you look at it, if you're really trying to amplify your signal by thousands and thousands of times, the operational amplifier is a better option for you versus the transistors. Okay, but also again, I'll show you there's a way to increase this amplification using the transistor when we use the transistor in a different configuration.